Uh-oh. All right. Well, welcome to the April OCRA members meeting. Switch mics? No. Yeah, well, it's not hard these days. I figured I'd start off with a little bit of trivia. After watching the splashdown the other weekend, I was looking through a number of videos online and saw one about the Mars rover. And apparently, I think it was manufactured by Jet Propulsion Laboratories. Initially, they wanted something on the wheel that would show up once a rotation so that they could just count how many times that showed up and they could tell how far the rover traveled. And of course, their initial idea was to put JPL on the wheel. NASA decided they didn't want the letters JPL showing up all the time. So they asked them to change and put something else on the wheels. So they came up with a series of holes and slots. And for 3 of the treads, those holes and slots would appear. Well, apparently, about the time they had it on the launch pad ready to go, somebody figured out that those holes and slots were Morse code for JPL. So I thought that might be a good opener for this evening. We'll start off with roll call. I'm Boyd Hudson, KO4GJO from Hillsboro.
I'm Paul, N2XF from Butner.
I'm Dave, NA4VY from Mebane.
Karen, KG4YJZ from Efland.
Steve, KZ1X from Chapel Hill.
Dave, K4DJW, Rougemont.
Dave, W4SAR from Efland.
Juan, KR4EQW from Mebane.
Ben, KO4BHX from Rougemont.
Sam, 4VWG from Durham.
John, KM4MDR, Eflin.
A lot of Eflin tonight. W4FK, Bob, Hillsboro.
KR4GOK, John from Burlington.
Ron, KO4RON, Pittsburgh.
I'm Matthew, KQ4ZYW, and on Zoom, we have George, KF8CNA, JR, and 4JQR, Ken, KO4DHJ, Fred, KN8CNA, wait, hang on, sorry, Fred, KN4QBZ, sorry, copied your call sign down wrong, Charles, KQ4TNF, Jerry, KR4NJ, Bruce, N1LN, Mark, KR3AM, Ryan, N7RYN, Aurora, and let's see if anyone else has popped up. Nope.
Wilson, W4BOH, Hillsboro.
I think we can go right to the presentation tonight. I don't think we had any officers report to anything. Bob? All right.
Dick and Wilson could probably join in on this too. April 25th, DFMA is having a picnic. OCRA is invited as always. We've also invited Triangle Mutual Aid, and it's in conjunction. It's at Bennett Place. It's in conjunction with the 161st anniversary of the largest Civil War surrender in the Civil War. We're going to have a period time communications exhibition, and Wilson's going to be involved in that using sounders, I believe. You want to
old time telegraphy with clickers, codes, and sounders.
And to
So
sign up,
if some people would learn Morse by clicker, it would be nice.
and sign up sheets back here. We just ask how many people you want to bring and ask that you bring a covered dish. The club will provide hot dogs and water. So if you want sodas or whatever, go ahead and bring those. And it'll be on site. So there'll be lots of exposure for the clubs. So hope to see you there.
I have a quickie. For sale tonight. To benefit the club now, not me, the club, we have a 3 cable set for component video, which I know that nearly everybody uses now. And they're gold plated, so if it said Monster on them, they'd be $50. But they say something else like professional. So they're $5. If anybody could use some gold plated RCA cables.
I have one thing also. The Parks on the Air event that we're doing with DFMA. The plan is for May 2nd and May 3rd if it rains on that day. We're thinking about around 1 p.m., but the shelter that we have reserved for all day on both the 2nd and the 3rd. So if you want to show up early, and I think some people are going to show up early, you can. The event is going to be at the Little River Regional Park out between Durham and Orange County. And I think that's about it for that. I can't think of anything else. If you have any questions, let me know. Aurora can also answer some questions. Yes, there are 2 pavilions if you show up at the park. It is the smaller pavilion. If you kind of follow the pathway, there's a big pavilion on your left with a playground. Just keep kind of following it and then kind of go to the right, and there's a smaller pavilion kind of in the woods. That's the one that we have rented. Yes. Someone asked if there was power there. Yeah, there are outlets. We're not sure if they're turned on. I can go test them pretty soon. Yeah. John, do you have a question?
Together, pine trees, so not a lot of open space around the bay. I want to contemplate what you plan to do during that.
Yeah. John recommended checking it out beforehand. The pavilion that we have rented is in the woods. There's not a really lot of space outside of that between that and the tree line. So if you're thinking of like a big antenna that would require a lot of space, that probably wouldn't work. Wilson, what's your question about POTA?
Doesn't it have to be battery powered?
It does not have to be battery powered. I don't think so. Yes, so it does. There was one more thing that was asked, and now I can't remember what it was. Yes, we will need the field day laptops. Do you want me to grab it? Yeah, I can grab them. Okay, yeah, we're going to be using the same computers that we use during field day because we want to get people used to the logging software that's on those laptops, and this is kind of a practice test before field day so people can get used to that. Oh, and I remember what it was. Bob mentioned that there was a grill there. So if you want to bring some food to grill and stuff like that, you definitely can. As Wilson says, ham stands for have another meal.
I suspect there are folks there that doesn't know what POTA means.
And they also ask that you take your ashes out and leave them in the grill. I also have pictures of the pavilion if anyone wants to see them on my phone. And you want to answer that, or you want me to answer it, Matthew? POTA. POTA stands for Parks on the Air. And there's lots of information on the internet. The great site is POTA.app. It's not an app, but that's the web address. And you can look and see what parks are being activated on what frequency. That's very useful if you're a hunter. So back to Boyd.
Any other announcements? All right, we'll turn it over to Ben.
Good there, man. Hi, can you hear me okay? Good stuff. Right, I was asked by the board to give a presentation on HF propagation. So to start with the definition, propagation is basically how radio waves travel from a transmitter to a receiver. And that's influenced by the atmosphere, the terrain, and the solar activity. And this is what enables communication beyond line of sight via the ionosphere. And the propagation varies by frequency, the time of day, the season, and these things directly affect the signal strength. Next slide, please. Right, summary of the talk. So a lot of the material I got from this talk was from this recent ARRL publication, From Here to There. Highly recommended, it's a good read. So my talk is going to cover antennas and radio waves, the sun's influence on propagation, how the ionosphere works to enable propagation beyond the line of sight, space weather and ham forecasts, and how you can get information about current conditions of the ionosphere. Prediction programs, how you can get a reliability chart, how you can work out where your signal is likely to travel at any given time of day. How to directly observe propagation in real time, so to see who's on the air at any given point. And then finally, home experiments, experiment I conducted during the 2024 solar eclipse. Next slide, if you could please. So what I'm not going to cover, so it's a huge topic. So I'm going to restrict myself to HF, which is 3 to 30 megahertz. I'm not going to go for very low frequencies or up into VHF and UHF. There are many great modes outside of the HF, but there's too much material to cover. So I'm not going to cover things like meteor scatter, auroral propagation, tropospheric scatter, EME, all those sort of good things. Next slide, please. So why to study propagation? Well, it's a key part of radio know-how for HF. Conditions are constantly varying. It's not just like using a handy talkie over line of sight where you can pretty much be guaranteed of making contact at any given time. So it determines when and how contacts can be made. Can you talk anywhere, anytime with enough power? Well, power certainly does help get into marginal situations, but you're not going to make propagation when none exists. The study of propagation is not an exact science. It's definitely, you can make predictions, but they're generally statistical in nature. And you need to take some account of what's happening on a daily basis. And I think is where a lot of the magic in radio resides. It's an interesting topic. Next slide, please. Right, so the building blocks of propagation are these 6 things on the left here. So how a radio signal travels through the ionosphere. So you've got reflection, which we're all familiar with, of course, the angle in equals the angle out. Refraction, which is where when a radio wave changes from one media into another, it bends. So like you see a drinking straw in a glass of water, as it enters the water, it appears to bend, as do radio waves as they travel from one layer to another of the ionosphere. Transmission is just literally transparent, traveling straight through. Absorption is where you lose the signal as it passes through a medium, and the loss is to heat. Diffraction is like knife edge diffraction in optics, where when a wave encounters a knife edge or an obstacle, it spreads beyond it and is deflected. And then scattering, which is basically a reflection in all directions, which is, why the sky is blue. You're not seeing stars during the daytime. So the start of propagation is from the radiating element of the radio, which is of course the antenna. And the self-propagating wave is created by accelerating currents linking to the electric and magnetic fields, and that then spreads out to become a self-propagating wave. Next. And these waves will travel in a straight line without anything hindering them in the way. So the first type of propagation is ground wave. So this is a surface wave that travels along the interface of two media. So that could be the air and the ground. It can also be two bodies of air, such as a weather front or something like that. It's a diffractive wave, so it is bent around the curvature of the Earth. You want vertical polarization for ground wave. These are best on the lower frequencies, as you can see from the chart here. So 80 meters or 160, you'll get out to about 60, 70, 80 miles. But for 10 meters, you're only going to be going maybe about 10 miles. Well, I don't know, it helps that much, does it? Yeah. I did have a whole set of charts at the end of this slide that show that you don't gain that much. You can go a little bit further. So ground wave is pretty limited. You can do local communication maybe from here to Durham, but you're not going to make Greensboro, I think, for the most part. Yeah. Yep, so that's ground wave for you. So next slide, please. So a little bit of history here. So the first person who managed to go beyond the ground wave was Marconi. So he was transmitting from this beach in the lower part here. This is Poldhu Beach in Cornwall. It's very familiar to me because I actually spent my childhood summer holidays just about a mile away from there. And this building on top of the cliff here is where his transmitter was set up. And he was aiming, he'd done several experiments in the UK over some tens of miles across the Bristol Channel. He'd made it to Ireland, and he wanted to try and get across to America because competing with the telegraph cables via radio waves. So it's not terribly well documented what he did, but they had a lot of trouble with the antennas. They kept blowing down. They're about 200 feet high. So they managed to get two masts set up about 200 feet high in Cornwall, and they had to use a kite at the receiving end because, again, they had storms blow the antennas down there. And he was on very low frequencies, so it was a spark gap transmitter. The frequencies, that's very broad range frequency. The frequency he was transmitted at, which wasn't even recorded, was set by the resonance of the antenna. So from the length of that, they think it was about 350 meters signal, 850 hertz. And he did this in the daytime, which is quite remarkable because it's not the best time of day to pick for that sort of low frequency signal. But it was reported that his signal was heard in Newfoundland, and that was the first long distance beyond line of sight radio transmission. And it was only the year later that Oliver Heaviside proposed a conductive layer within the atmosphere that channeled the radio waves between the sky and the Earth. And that would have the conductivity 10 times that of seawater. Next slide, please. So the losses of propagation. So the first thing is free space attenuation. So a radio wave will carry on in a straight line indefinitely in space, for example. But every time the distance doubles, the wave spreads out. So you end up with just a quarter of the power. And within the ionosphere, given that you can't go line of sight because the Earth's in the way and you don't want to go out into space, refraction, all of the factors that contribute to refraction will also have an attenuating effect on the radio wave. Lower frequency signals are absorbed far more than higher frequency and in inverse square. And also multi-hop reflections, also very lossy. Right, the sun. So this is a picture of an eclipse. If anyone's been fortunate enough to actually see one, it really does look like that. It's quite spectacular to see the corona. So you're looking at the sun's disk obscured by the moon there, and you can see the amount of material being ejected off the sun. So the sun has both beneficial and detrimental effects on the ionosphere. The quiet sun emits ultraviolet light and X-rays that are essential for ionization, for the ionosphere to be able to conduct. But it can also be detrimental when the sun becomes active. You can get coronal mass ejections and flares that can be very disruptive to the propagation. Next slide, please. So the solar cycle, so every 11 years on average, and it can vary from 7 to 17, you'll see a peak in the sunspot cycle and then back down to the minimum again. And we are just either at or maybe just past the peak of cycle 25. It's not clear whether or not we may get a second peak. I think the sun is split into two hemispheres and they can sometimes be slightly out of step, but I think we're now getting towards the end of when a second peak could potentially occur. So likely on the downward slope now. At solar minimum, you can have many days when you may have no sunspots whatsoever. And at solar maximum, that can go up to, I believe, about 250 sunspots. And sunspot numbers are not just a literal count of the spots, but they're calculated from the number of groups multiplied by 10 plus the spot number. So the solar cycles are quite variable in themselves. They've been constantly observed since about 1750, recorded on a daily basis. There's been minima, there's been a modern maximum that I'm told just ended in 2002. So we're now maybe in a lower level of solar maxima. So the quiet sun. So this is a picture of the sun taken in hydrogen alpha, I believe. And you can see here that these are the regions of sunspots. They tend to form into two groups that are linked with magnetic fields between them. They were first observed a very long time ago in China and Korea, getting on for 3,000 years ago. And they're cooler areas associated with magnetic activity. And it's not the sunspots themselves that emit the ionizing radiation, but surrounding them are these plages, beaches, that are the areas that release the ultraviolet light that is ionizing. And these sunspots can persist. The sun rotates on average once every 27 days. Because it's fluid, it's slightly faster at the equator and slower at the poles. And these sunspot groups can come round repeatedly. So you can see them again, a month later, which plage French for beach. Yep. So how can I calculate is groups times 10 plus the number of spots. And the smooth sunspot number, there are a number of different numbers available for sunspots. The smooth sunspot number is a 12-month average, which means that it's actually, the average is 6 months behind the current day. So you're looking very much back in time for that. And there are other sunspot numbers that give you a more immediate result of what's happening at the moment. Next slide, please. Sun also can have the detrimental effects to propagation. So these would be solar flares. Solar flares are instantaneous. They travel at the speed of light. Technically, they take 8 minutes to reach Earth, but seeing as nothing travels faster than the speed of light, the first thing you'll know is when they arrive. They can last for minutes to hours. They're recorded as C, M, or X, and each one is a magnitude higher. So the X flare is much more powerful than the M, which is much more powerful than the C. They are X-rays and EUV, and their effect is to increase ionization of the D layer, which will then absorb radio signals. The other features that can be disruptive are coronal holes, which are dark unipolar magnetic regions. And these allow the solar wind to escape. The solar wind is particles with an embedded magnetic field. And when that magnetic field interacts with the Earth's magnetosphere, it can have a detrimental effect. Similarly, coronal mass ejection, which you can see up the top here, is quite literally what it says. It is an ejection of material from the sun. And these take some time to arrive, 24 to 36 hours. You do have some advance warning of those arriving. Those will affect both the night and the day side, whereas the solar flares are instantaneous and they're just affecting the sunlit side. So the solar wind, the direction, so the solar wind is described as having the three axes, X, Y, and Z. When the solar wind in the Z-axis is southward, it's rubbing contrary to the Earth's geomagnetic field, and that's when it causes maximum disruption. So a southward or negative BZ is very detrimental to the Earth's protective geomagnetic field, and that's when you'll find the aurorae come into play and electrons slough off into the poles. Yep, next one. Right, so the indexes that you can get of solar disruption, A and K index. So the A index, well, it's not the K index. So the K index is the previous 3 hours on average, and it's a point measure. The KP is planetary, and K index is just for one specific site. Log scale from 0 to 9, low is better, but very important also is the trend and the direction which it's heading. So a rising K index is very bad, but a lowering K index is good, irrespective of the value. K is a single location reading, as I said. The A index is an average of the last 8 K indexes. That's 24 hours. So it's a forecast of what the condition is going to be like yesterday as a result of that. I'm sorry? Well, this is actually direct observations. This is not prediction. This is what has happened in the last. So these are measured with magnetometers, basically a compass that looks for deviation in different places around the planet. Yeah. Yep. For the KP index, it's averaged around the planet. Yep. And the A index is averaged over the last day. So yeah, this is historical. You can get a future prediction of this, but that tends to be a little bit vague, partly to do with the sun's rotation. You kind of know what's coming in the next days because of what happened 27 days previously. So the A index is linear scale, 0 to 400. Again, you get the A and the AP for planetary, which is the averaged out value for that. So those are the two indices. Solar storms disruption. The K index is far more useful for what's happening right now. Next slide, please. So this is a useful website that contains just some of the basic information about current solar conditions, solarw5mmw.net. On this, you have the sunspot number, which is useful to know. I think that's the current sunspot number. You have the observed solar flux. This is the amount of 10.7 centimeter radiation emanating from the sun, which is a proxy for both the number of sunspots and for the ionizing radiation, but it's what you can actually measure at the Earth's surface. So mostly of historical value. Now we have satellites that can measure directly, but 150 or higher is better. I think that one goes up to 300, and it accumulates. If you could have a high solar flux for 3 days or more, that's very beneficial. The geomagnetic storm, that's the K index or the A index. You have on the left here conditions for bands currently, both daytime and nighttime. And as you can see here, here's a chart. So the dark lines here are the actual measured, and the pale lines are the predictions. And as you can see, sometimes they're fairly spot on, and other times there's large differences. So prediction is definitely not an exact science for what's occurring, but you can get an idea maybe of what's on the horizon. Next slide, please. So this is the 10.7 centimeter flux. The Earth's atmosphere is transparent at 10.7 centimeters, so it can be measured directly from the Earth's surface. But 2.8 gigahertz is way too high of a frequency, or too low of a frequency, sorry, for ionizing radiation. So it's a proxy. As you can see, it's well correlated with the sunspot number. And these two things themselves are very highly correlated with the amount of UV and X-ray radiation that's ionizing the atmosphere. So the ionizing radiation is 0.1 nanometers to 100 nanometers. And this frees electrons from the upper atmosphere gases. A constant flow of this is needed to overcome recombination. So as the gases are ionized, they will want to recombine, which is why daytime levels are so much higher than nighttime when things start to recombine. Closely correlated with sunspot number, 72 hours. And then this is a chart of the gases in the upper atmosphere. So at sea level here, we have mostly nitrogen with some molecular O2 oxygen. But as we get up above 100 kilometers, we start to see atomic oxygen, just O as an ion increases. And then above this, as the oxygen drops off, helium becomes more dominant. The lighter fractions are going higher. And then we have hydrogen. I expect hydrogen to go right up, but hydrogen will achieve the escape velocity and just get lost out into space. So this becomes important later, that we have molecular oxygen down low, but we're getting atomic oxygen higher up. Next slide, please. So the ionosphere. The ionosphere is created by ultraviolet light and X-rays as they shine from the sun. So an ion is where an atom or a molecule which has a positive core of protons and then a negative shell of electrons. Ultraviolet light from the sun will provide the energy to take one of the electrons and ping it out of the shell of electrons that surround the atom. So you end up with a free electron and then a positively charged ion. Now, those can recombine, but as the gas becomes lower pressure and more spread out, it takes longer and longer for the ions and electrons to recombine. There's slightly different wavelengths responsible for ionization at each level. The F layer, longer wavelength, 10 to 100 nanometers, and the D and E layers, which are lower down, 0.1 to 10 nanometers. And on the left here, we can see that the F layers are up the top. During the daytime, you get the F1 and F2 layers. They will recombine into just a single F layer at night. And the lower layers, the D and E, tend to disappear at night. At least the D layer recombines very quickly and the E layer tends not to persist. The F layer, being at a much lower pressure, takes much longer to recombine, and the ionization can persist on after sunset to some extent. Just give me 1 minute to check my notes. Previous slide again, please. So the constant supply of radiation is needed. The F layer recombines very slowly. Radio waves entering free electrons are refracted. So as a radio wave enters these regions of free electrons, it will tend to bend away from the higher density of electrons back down to Earth. Refraction is gradual. It occurs over tens of kilometers. And it depends on electron density and the frequency of the radio wave, with bending increases with longer wavelengths. So they will be bent far more. Next one, please. So this picture has been in the news recently. It was taken by the Artemis 2 crew just about a week ago. And I thought this was great to give some sense of scale of just how far a radio wave has to travel in such a thin layer of the atmosphere. So this is actually taken from the night side of the Earth, and it's upside down compared to what we're used to. You can see the Sahara, North Africa. Spain is over here. This is South America. You can see the Aurora Australis and the Aurora Borealis here. These are at about 150 kilometers height. And you can see the atmosphere here. This is the troposphere where the weather takes place, and the stratosphere, which is up above the moisture carrying layer of the atmosphere. And you can see how very thin this is. Only the D layer is within the atmosphere as we know it. So the 99% of the atmosphere is below 50 kilometers. The D layer starts really at the top of that, up to 90 kilometers. The Kármán line, which is an arbitrary designator of where outer space starts. This is where Jeff Bezos's ballistic rocket launches made it up to. The E layer then starts really in outer space. So you're looking at the E layer really just about on top of this white line. And then the F layers are just out into outer space. So starting at 150 kilometers and going up to about 600 kilometers. And it's interesting to consider that the International Space Station orbit is 400 kilometers. So when you're making radio contact with Europe or South America, your radio waves are right up there orbiting with the space station before they're bent back down into Earth again. Yeah. Oh, so the molecular oxygen is important because it has 1,000 times greater recombination rate than the atomic oxygen, as we saw in that chart of the different gases, where you just have the O on its own. The recombination rate of the electrons with the ion is 1,000 times slower than it is with the molecular oxygens, which means that at the D layer, you're seeing recombination of the ionization much more rapidly than you are high up in the F layer. Right, next one, please. So the lowest usable frequency. This is the lowest possible frequency you can use for communication. It's a variable threshold, and it's determined by the amount of D region absorption. So the D layer being the lowest layer where the recombination rate is the highest, this will tend to absorb low frequency radio waves. And the lowest usable frequency will be determined by the degree of ionization in the D layer. And the question is why? Why is D region ionization bad and F good? Well, it's because when a radio wave is interacting with an electron, there's a much greater chance of it recombining with an ion in the D layer than up in the F layer. It either recombines with the ion or it can bump into a neutral ion. And if the radio wave is interacting with that electron while that recombination takes place, then the radio wave's lost to heat. Whereas up in the F layer, there's much more chance of it just being re-emitted and continuing on its way. The lowest usable frequency can be higher than the maximum usable frequency at some points in the day, and that's where there will be no propagation on any frequency to a given region. And often there can be no good frequency when both places are at night.
So when they do this, I mean, this is basically when they're looking at the HF. But obviously, you can communicate with submarines at 15 kilohertz.
Yes.
You got that power.
Yeah.
Big enough.
Yeah. Well, I mean, the very low frequency radio waves will penetrate deep down into the ocean. They have, that's why I stuck to the 3 to 30 megahertz, because we're,
HF, 2 to 30 megahertz, this is the lowest.
yes, yep, yep. Yeah, bear in mind, we're talking about the ionosphere here. So this is not going to affect the ground wave. This is not going to affect, anything that's going down sort of through the water or the rocks. This is purely about signals that are, and it's not even talking about the critical frequency and the vertical radio waves. We're talking about oblique launches into the ionosphere that we want to be refracted back down to Earth. So it's about sort of traveling the surface of the Earth around it. Yeah. Okay, next frequency, please. Takeoff angle and antenna height. So this was an interesting plot I found that talks about, so if you have a dipole, we normally think that a half wave is the best height to have that at. That's this here. So each one of these plots is for a dipole at different heights above ground. And as you can see, if you're really down low at 0.1, 0.15, this inner circle is showing that you're getting a lot of signal attenuation by just being coupled to the ground. By the time you hit 0.2, you're actually getting most of your signal radiated, but it's going vertically up. And then as you increase the height, you get this bifurcation. So the signal's beginning to go off now to the sides. And once you hit 0.5 of a wave above ground, that's when you're getting the best out each side, not going directly up. And then if you go higher yet still, you start to get additional lobes developing. So once you go up to 0.6, you're starting to get radio waves going up and out. And then as you see, as you increase all the way up to 2.5, you start to get multiple lobes, which may help or hinder you. You're likely to have places you're not going to be hitting, but your signal is going to be distributed around the place a lot more. So it depends what you want to do. If you pretty much never want to be below 0.2 because you're just going to be warming the ground beneath you. 0.2 is useful for near vertical incident sky waves. So if you want your signals to go up and then come straight back down again, you want your dipole low, because then things are going to be aiming straight up and coming down again. If you want DX, you want the lowest possible takeoff angle. So half a wavelength would be good for you for that, because that's going to send most of your signals out to the side. And then once you get too high, you start to see this fragmented pattern, which is then just a roll of the dice, whether you happen to get lucky with well, a vertical antenna is an entirely different deal. Yes, that is going to send stuff out to the sides pretty well. That's going to be good for DX. But this is really just a setup for the next slide, which is going to talk about the NVIS. So I wanted to just make the point that if you want signal going up, you want a dipole fairly low to the ground. So next one, please. So the critical frequency, this is also known as FOF2, and this is the highest frequency that the ionosphere returns to Earth when transmitted directly upward. So this is measured directly with ionosondes. There are about 150 of them spread around the world. And this NVIS is very useful for short local range. So as we'll see later, as you go up in frequency, you can quite often get a skip zone where your ground wave will only get you so far, but the signal return from the ionosphere is going to be much further out. So you have a whole region that can be half a continent's worth of space where you just can't really get to. So the critical frequency, 3.5 to 7 megahertz often 40 to 80. It can bridge the gap between the end of the ground wave to the skip zone. You want your signal going pretty much straight up for it. So anywhere from 90 degrees to about 60 degrees launch angle. And that will give you regional communication within about 300 kilometers of where you're transmitting from. You want to be operating during the daytime, you want to be operating as close to the critical frequency as you're able to, because as you go lower, the attenuation by the D layer gets higher. The NVIS is straight up, so it's punching through the D layer in the shortest distance possible. So it does tend to go through. It will be refracted and returned back down to Earth in a region. At night, you want to go for longer frequencies. The D layer will disappear and becomes less of an issue. Right, next slide. Oh yes, here we go. So this is MVIS. So here you can get a propagation map. So this is a very nice website here. I have the frequency, the webpage on it. But as you can see, MVIS, this 40 meters during the daytime, 40 meters is short. You're getting your state and neighboring states with it, which is pretty good. And as you can see on this, this is a reliability plot. So we're getting pretty much up to 100% reliability within a state's radius or so. So as we can see, that frequency, if you tried to send it off in the oblique angle, will be passing through a lot of the D layer and will get very much attenuated. But when it goes straight up through the D layer, it can pass through in quick time, come back down again. Yep, and that will get you communication with no skip zone during the daytime. All right, next one, please. So the maximum usable frequency. So this is now going to be important for DX. Again, very variable, determined by the level of ionization, the distance between the transmitter and the receiver, and the launch angle, the angle that you're sending the signal up into the ionosphere. Yeah, so the frequency will increase with distance. Oblique angle is required for this. It's variable depending on heading. So the highest direction is in the direction of the sun. So in the morning, it will be to the east, midday to the south, and in the evening, it'll be to the west as the sun proceeds around. And it's most efficient to work as close to the maximum usable frequency as you're able to. So if you pick a frequency that's 0.85 times the monthly mean, you should have a 90% reliability of making that contact. And I can certainly say that, if you can get up near 10 meters or something, if it's open, then you can really work the world on 5 watts without too much trouble. Next slide, please. Right, so this is ionospheric refraction. This is a reliability plot of the 10-meter band, as I was saying. So this is for a transmitter located here in North Carolina. You can see the ground wave on 10 meters is really not going to get you very far. But because of the high frequency, your signal is not going to be returned. If it goes off at too high an angle, like A and B in the diagram here, it will just make it out into space. You're not going to get that signal returned back down to Earth. So C is the critical angle. That's the angle at which the signal will be returned. But as you can see, there's a whole skip zone from the transmitter to this first bounce here, and you can see that in the plot. So great for talking to folks in the Caribbean, but you're not going to make it to Virginia or Tennessee very easily with 10 meters in the middle of the day. Well, bear in mind, this is going to move around with the sun. So this is taken at about midday. And there's quite a few interesting things to look at in the plot. So this is from vocab, where you can put in what your antenna height, your takeoff angle is, your transmitter power. You can sort of set it up to your individual setup. And it will give you a prediction based on the model of the propagation that's within that. And this is again reliability. So we're looking at the dark red color here is close to 100%. And then as the colors change down the chart here, we're getting less and less, down to about 10% here for Antarctica. So what we can see is multi-hop. So we've got 1 hop to the Caribbean. If we get down here, we will have taken 2 hops and then 3 hops to here. We can see this persistence of ionization into the nighttime here. So, the night moves from east to west. So what we're seeing here is ionization that's remaining within the ionosphere after sunrise, which is the interface of the light and dark areas here. And we don't see the same thing on the other side at dawn, because of course that's the point of lowest ionization. So we can get multi-hop here. So we've got C goes into C1, and then a lower angle yet again. And we may find that we can actually travel further out, up to a maximum of about 4,000 kilometers for one leap. Yeah, right. So F layer propagation. So F layer is the top layer, and this is the one that is responsible for most most common mode for DX propagation. The recombination of electrons with ions is very slow up at these heights. So we can have multi-days of good solar flux can really get that ionized nicely. You can get ionization, particularly at the peak of the solar cycle, persisting right into the night. It's the layer that's most affected by activity of the sun. So it's highly variable, and a signal from the east coast of the USA to Europe, the maximum frequency that will be refracted can vary greatly from 7 to 70 megahertz. So you really do need to be paying attention to what the propagation is to decide what band you want to be on for that. As we saw, the F2 layer is high up. It's at 250 to 400 kilometers. This is above the layer of space, basically, which is 100 kilometers. Each hop, so the maximum hop you can achieve is about 4,000 kilometers in one go. There are other modes that will take you around the world without coming back down to Earth. There's the Peterson ray, and there's whispering gallery modes that can do chordal hops whilst remaining within the atmosphere. You can also bounce off the top of the E layers. There are other routes that can be taken, but if you're doing a ionosphere back to Earth, back up again, you're doing a series of 4,000 kilometer hops. We've already talked about the MVIS, so that will give you your first 300 kilometers or so beyond the ground wave. One of the interesting things is the winter anomaly. So in winter, you'd normally expect ionization to be less because we're tilted away from the sun. The sun's at a lower angle. But what we actually find is that ionization is 4 times higher in winter than it is in summer. And that's because you're getting more atomic oxygen in the atmosphere at those heights than you are during the summer, which allows, of course, a much slower recombination rate. So winter tends to be a good time for.
If single hops at 4,000, how would I tell me 2,000 kilometers?
Oh, a maximum of 4,000. Yes, you go a little bit higher as long as the frequency will get returned. Yep. Yeah, so that's the maximum. Mm-hmm.
I mean, a lot of people want to get their tower as high as possible.
Mm-hmm.
Size matter. It'd be too high.
Yeah.
Yep.
So for each length of pop, there's an optimum tower height, which matches the takeoff thing.
Yeah. I was thinking about, yeah.
Just said.
Yeah.
Sorry, I was talking about the relationship of tower height and takeoff angle and skip distance, and saying that the tower can be too high, even though everybody wants to have the highest one in the neighborhood. For every skip distance, there is an optimum takeoff angle to get that first hop to come down to the earth where you want it to.
Thanks. Well, well, it depends. If you want to do 160 vertically, and you do want to do 160 vertically, then I guess that's what's determined the height of the tower. I think, yeah. I think, and also what I was talking about was dipoles, of course. And if you have a directional antenna, that's going to be different yet again, because you're going to be narrowing your beam width to some extent.
All the takeoff
Still the same.
That height.
Yeah.
Optimum height for dipole.
Yeah. Okay. Fair enough. So yes, I think you can be too high. It's interesting. I mean, there are antennas like the NorCal doublet that give the exact same pattern for every frequency. When you put it in, it uses a combination of the feeder and the doublet to achieve that. But of course, you're fixed with your antenna height. You're still not going to achieve quite the same pattern off the back of that. So the maximum usable frequency is pretty much a direct function of ultraviolet light, how much ionizing radiation is reaching the atmosphere. So when you've got a high point in the solar cycle, when you've got full noonday sun, you're going to have the highest maximum usable frequency. And there's a time delay as well associated, of course. The circumference of the Earth, it takes about 0.14 seconds for a signal to transfer to travel around, and multipath fading. So if a signal takes two different paths, it can arrive out of phase, and if those phases, they can either add constructively, or if they're half a wavelength out, they will subtract. And of course, sunlight is needed for frequencies higher than 10 megahertz. So you have your daylight bands being the longer, the shorter frequencies, and the nighttime bands being the longer frequencies. Although I've got a few more things to say on that one. Yes, the F layer has the highest electron densities of any layer. At any point in the frequency in the solar cycle, you may only get at the low point a few hours above 14 megahertz, but at the peak of the solar cycle, you can have many bands open right the way around the clock. The Peterson ray will allow you to go beyond this 4,000 maximum hop up to 12,000 kilometers per hop. And I've got the multipath cancelling out. Yep. Right. Next slide, please. So, of course, there are two ways to each destination. Of course, radio waves travel in a straight line. You can get skew and scatter, but for the main propagation mode, we're talking about just the great circle direct path. But of course, you can go the long path or the short path. The short path is always less than 20,000 kilometers, because that would be for the two most distant points. Sunlight, of course, is required above 10 megahertz. So if you're on a higher frequency, you'll be wanting to take whichever path is during the sunlit side. But you can also get useful things going on the night side, particularly this caudal hop mode that you can see going on here, where the refraction is actually not returning back to Earth, but it's just bouncing around the inside of the ionosphere. And those night paths can avoid blanketing and absorption from the D and E layers, and even the F1 layer can blanket the F2 layer. Daylight paths can, of course, be on a high frequency, which is more efficient. But the one thing about long path is that it will require some coordination potentially between the transmitter and receiver, because, of course, you naturally would probably go for the short path, and you'd both have to have your antennas pointing in the opposite direction to hear each other with the front to back ratio if you were looking for a long path connection. Next slide, please. Right, another of the more specialist modes is gray line, which is a twilight path, the terminator, between night and day, right the way around the Earth, dawn on one side and dusk on the other. Is a special zone that can allow for easy communication right the way around that line. And it has the advantage that the D and E layers, being more dense, disappear very rapidly, but the F layer will persist with its ionization. And it also, because it's higher, it will tend to remain in sunlight longer as well. So you've got a double bonus there. It's also variable. So given that the Earth's got a 23 degree tilt, it's north and south only at the equinoxes. So it will actually give you a 46-degree segment of the Earth as the year progresses. You're getting slightly different contact potentials each day as it gradually changes throughout this segment. And there's a lot of debate about how the grey line actually works. I think the current thought seems to be that signals actually skew through the night side and may be sort of bounced back around by different layers. But that's your grey line. So to take this from the view of frequencies, so of course, two inputs to the propagation are both the electron density, but also the frequency which you're transmitting. So for the longest bands first, the 160 and 80, these suffer the most from daytime D-layer absorption, exponentially so. So you're going to get far more absorption of these during the daytime. They also suffer very strongly from interfering noise from thunderstorms and man-made noises. 160 particularly also has a difference in the ordinary and extraordinary waves, which are the two different polarizations of radio waves. And the Earth's magnetic field will tend to impact one of these more over the other. So for 160 in particular, and we're coming on to antenna height here, by far the best is to have a vertical takeoff for 160, I believe. And you may even want to do a vertical to transmit to a beverage receive on that. Coming up in frequency, the 60 and 40 meter bands, these tend to go short during the day. So as long as you are below the critical frequency, these can be great for doing that vertical instant sky wave out to about 300 kilometers. You have to keep an eye on what the particular day's critical frequency is. During the daytime, you want to be up near the critical frequency and down lower at night. These are less affected by thunderstorms and seasonal noise like that. And they tend to be open all seasons and all points of the cycle. So 40 meters can be pretty good for making worldwide contacts in less than ideal conditions. Then moving on to 30 meters, this is when you then get the transition from daytime, nighttime. So 30 meters will go a lot further during the daytime. You get about 3,000 kilometer radius. You can get the whole continent in one go. There tends to be a skip zone introduced at about 30 meters. And you can really make it all around the nighttime of the Earth at night. The propagation plots are quite good for 30 meters. Higher again in 20 and 17, this is now getting into the primary DX favorite. So these are primarily more daytime bands, although at the peak of the solar cycle, you'll find that the ionization will persist through the night and allow communication to be conducted through the night side as well. And the skip distance now becomes more present. So the angle at which you're entering the ionosphere means it's not going to return close to where you are. So by the time you get to 20 meters, you're looking at a significant skip zone. Yes, yes, significantly, yeah. 15 meters has been fantastic recently. Prime DX at solar maximum, and it's been very interesting to watch who's on air and how people can shift down to 15 meters as the ionization is very good. It's much more sensitive to solar activity. So, you know, if you're up at the solar maximum or you know, having a particularly good solar day, it can be great, but then it may well be closed or a daytime only band off peak. And then 12 and 10, well, extreme variation. So it can be very efficient at the peak of the cycle. And I've certainly made some contacts in the last year on 10 meters that seem nothing short of miraculous, certainly QRP going a very long way. But equally, when it's closed, it's closed. Definitely closed at solar minimum. There was nothing about 3 years ago. But it's really getting up into the transition to VHF, and you get all sorts of more exotic modes starting once you get up into 10 meters, sporadic E and all sorts of reflection and other interesting modes that are kind of getting beyond the HF zone. But yeah, so that's by frequency summary. Next slide, please. So propagation predictions. So a lot of the models are very statistical in nature. There's huge day-to-day variation. And you can get models that are based on multi-day or month or longer. But these tend not to be you know, relating to today and whether or not you're having a good solar day or a bad solar day. So a lot of vertical ionosons worldwide for measuring this critical frequency. So they transmit a signal vertically up or a spread of signals vertically up and see what comes back down again. So you're measuring the signals vertically returned. So that would give you the critical frequency. And then the maximum frequency tends to be about 3.5 times higher than that. And there's global coverage of those. The prediction long range tends to be quite general and is based on monthly averages. There are a number of websites so you can get up-to-date information. Spaceweather.com has got a lot of information. SolarHam, hfradio.org. But there was an interesting quote in the book that I was reading, and it said, "It's easy to get overwhelmed with all the colorful and interesting to look at measures. And in the author's opinion, just knowing the level and trends of the 10.7 centimeter solar flux, sunspot number, and the level and trend of the K-index will give a good picture of HF propagation." So if you go on spaceweather.com, there's a side panel that has a huge amount of information. And much of it's useful, but I think if you just focus on those things in that quote there, I think well, I think you need to know those things, but not so much the others is the point. So, I mean, the 10.7 is going to tell you the amount of ionizing radiation, as will the sunspot number, that tends to be averaged over a longer period. The K-index will tell you about the disruptions. It's all very well having the ionization there, but if you've got the disruption happening as well, that's going to blanket that. And what else have we got there? And the trend as well, whether that's rising or falling. I think those are probably the most important values to pick out first from the multitude of interesting, colorful photographs you can get. Next one, please. So this is VOCAP. This was a great product of US taxpayers' money over many decades. So VOCAP's Voice of America, they started making observations and then models in the 1930s and came up with a program that will predict, model the ionosphere and where you can expect your signals to go. You can set your antenna, your power, your mode. You can set the date and time of day down there, your transmitting location. You can even put in a receiving location if you want, or you can just see wherever your signals happen to go. And you can get a number of plots out of it. So I've got on the left here a reliability wheel. So each sort of concentric circle is a different band. It does from 10 meters up to 80. They don't do 6 and 160 because they're quite difficult to predict with different factors at play. So it's 10 to 80. So I've set this up from our location here in North Carolina. I'm talking to someone in Sydney here to try and get an idea of where would be good to go. Put in information about my antenna. I've said CW 100 watts, for example, but you can change all that. And this will give you a good idea of which and what time of day would be a good option for making that connection. So you can see here, you'd be pretty good choosing times in UTC, but sort of 9, 10 o'clock at night on 17, or maybe 8, 9, 10 in the morning on 20 would be good options. And around about 5 or 6 in the evening, well, you may as well just not bother. So it's a good way to get an idea of what frequency, what band, and what time of day you'd be best off if you're trying to make contact to a specific region. You can also get the gray line predictions from this, and the reliability charts I showed earlier with the multi-hop and the extension to the night side are also generated by this. So you can set it up for your location, your particular equipment, and you can get a good idea of either where your signal will get to or how to make a contact with a specific location out of this. Next slide, please. Oh, yes. VOCAP, VOACAP. So VOA, Voice of America, coverage analysis program, I think, something like that. VOCAP.com.
Ben,
yep.
Can I butt in again?
Yep.
This is great stuff. The DX spotter programs like DX Summit, and there are several, and I know nothing about any of them except DX Summit, have the ability to show you the VOCAP prediction for any station that you want to see. So you don't have to enter all this stuff. You go into DX Summit, you find a station that you might want to call and click on him, and you'll get the option of his location in QRZ or propagation to him with the wheel.
I think it's the model that's become quite widely used. So it's only recently been put online. You can actually download it as a Windows program. or you can just use this, which is the web interface, and I believe you get the same regardless of what you do. The project was taken over by let me see if I can find the names. Yeah, Greg Hand was the person who translated it from the original Fortran into a Windows-based program. And then a Finnish gentleman by the name of Jari Periomäki has developed this web interface. And it's pretty easy to use. You literally just go down through this menu, select your mode. You can have SSB, CW. I think they have digital. Select your power level anywhere from 1 watt up to 1500. You can enter your antenna. You can say if you've got a dipole or a directional antenna, height above ground. You can put in more settings if you want, but that's a pretty good start. And then you can just set your transmit location. And then you can either do the rel charts or this wheel. It's a pretty useful tool, and it's great for just playing around with and learning about, how propagation differs by frequency, by time of day, all those sort of good things. Next slide, please. So the next thing I'm going to say, so it's all very well and good making predictions, but really what's best of all is just to actually directly observe what's occurring. So reverse beacon network is a fantastic resource. This is literally a CW skimmer that's listening from a series of listening stations on all bands. Will decode people calling CQ, and it will tell you where they're located, what frequency, and what their signal strength is. So I've got 2 plots here. The first one is at dawn, listening from North Carolina. And you can see the yellow traces off to Europe. So we're getting 40-meter contacts right the way through the nighttime zone. And we're getting 10-meter contacts, I believe, going over to Japan and down to South America. So I know that if I want to speak to someone in Europe, I'd be pretty well off choosing 40 meters. And if I want to get down to South America or Japan, 10 meters would be my choice and not the other way around. But now we move on 12 hours later to dusk, and we see pretty much the exact opposite. We're getting 15, 20 meters going into Europe and even into Asiatic Russia there. But now we've got the 10 meters, sorry, the 40 meters going down New Zealand, Australia, and Japan, and out to the west coast of the US in that direction. So this is a great way of really working out, not just from a prediction, but from actually direct observation, what is happening now. And literally you get people's call signs, you get their exact frequency to within, I believe, 100 hertz, their mode, their signal level, even what speed they're operating Morse code at. So you can even filter by how fast you want to go on that. And you can literally just in real time pick people off this list to make a contact with. So direct observation is a really great way to go rather than trying to predict where somebody will be. This is literally observing it in the instant. Next. This is RBN, so reverse beacon network. And again, you can do all sorts of filtering here. So you can filter by band. This is pretty much CQ only. You can get some beacons. There's the NCDXF beacons are available if you're interested in looking for those. But this is really for finding people doing CW. So you can enter the speed. You can enter the maximum age of the plot. So you can maybe just do the last 10 minutes or 15 minutes. You can set it to whether you just want people calling CQ or whether you want to just listen to anyone who's on that band. And you can filter out by band itself. Yep, so reverse beacon network, and I highly recommend that. And you can also put in whether you just want one particular spotter, so you can choose someone nearby in North Carolina if you want to get information for literally what's occurring right nearby. Next slide, please. So this is another alternative, which is Whisper. So this is now people transmitting just propagation testing modes only. So there's one way direction. So you're listening to basically a very low power transmission, less than 5 watts. And the signal's digital. It's a frequency shift mode. There are 4 levels, and each level is only separated by 1.4 hertz. So it's incredibly narrow band. This is a predicted, well, this is an example of what the transmission should look like. and it literally just encodes the call sign, the grid square location, and the power level. And that's basically the first 50 bits, and the next 112 bits are all about error correction of that first 50 bits. So it's an incredibly low power mode, but it's quite robust. It's very proof against error. So you've got these 4 frequency shifts, and here's an example of 2 transmissions in the wild, listened on a frequency plot. So 2 minutes on the x-axis, and probably just about 10 or 15 hertz spread that way. And again, you can see, so people tend to transmit on a cycle all the way up the bands over the course of 20 minutes and then back round again. So you can get an idea of where signals are getting to. So it's a similar idea to the reverse beacon network, but instead of it actually being people calling CQ, this is just a propagation test.
Are the 2 traces everything?
Well, because hundreds of people transmitting in a narrow segment. So the segment of WISPR is about 200 hertz wide, and everybody tries to pick a slightly different.
So they're stacked up.
Yes, yeah, they're two different people calling from different places. Yeah, and if you zoomed out, you'd see a whole bunch of these. And the timing is very critical. Everybody needs to, just like with FT8, you need to start and stop at the right time. So you really do need to have it within about 1 or 2 seconds of correct to get decoded. And you. Well, what we're looking at here, so we've got frequency in this scale. So we're looking at basically about 6 hertz spread here. And this is time. So, you know, I think presence here, and it's going backwards in time this way. Yeah. Yeah, basically. Exactly. Yes.
Square.
Yeah, we got away with the words. Yeah, so that's basically, that's WISPR for you. And, you know, maximum 5 watts, but minimum people go down way into the milliwatts. And it's amazing how signals do get picked up and decoded right the way around the world with very little power on WISPR, partly to do with this error correction. Yep, next slide, please. Right, so this is now getting on to an experiment I conducted 2 years ago. I traveled out to Arkansas for the eclipse and decided to take a transmitter with me to see if we could get a signal or any idea of what was going on in the ionosphere affected by the eclipse. So there was a project by the Ham-Psi group, who a combination of citizen scientists and a conglomeration of universities, mostly located in the Northeast. And they decided to look at the WWV time signal from Fort Collins to trace any Doppler shift in the time signal as it was transmitted. So that signal is broadcast on 10 megahertz very precisely. It's used as a standard. And what they found was that as the eclipse progressed, they saw a drop off in the frequency followed by an increase in the frequency before returning to normal. And this corresponded to Doppler shift because the point at which the refraction of the signal occurred shifted as the eclipse moved over. So as the eclipse moved over, the ionization level changed. The point of refraction, the apparent reflection point, shifted. And Larry Carr of Brookhaven National Laboratories took a look at this and actually made a calculation and said that given the frequency and the frequency shift, you could actually tell that the frequency, the point of reflection was moving at speeds of up to 15 meters a second. And it moved about 50 kilometers during the passage of the eclipse. So I did the exact same experiment from a campsite in Arkansas, literally just using a half wave end-fed antenna thrown in a tree. And this kit from QRP Labs, which is the U3S, which is a pretty nifty bit of kit. It's about $35 for the main transmitter and then $20 for the GPS. So just over $50, and you've got a homebrew ionosonde. And given that it's got the GPS, it's got an incredibly tight frequency control. So literally shifting by, well, what we're looking at here, so it's a dual frequency shift CW. So what you're looking at here is time, 1, 2, 3, 4 hour transmission the distance between these two tram lines here is only 4 hertz. So as you can see, there's very little variation. The GPS really does keep that very tightly controlled. It's got a temperature controlled oscillator in it as well. And what we can see is that before the eclipse, I'm just getting the 2 frequency shifts. So this is literally broadcasting my call sign once every 10 minutes, which just meets the requirement to have your call sign every 10 minutes. So it's over and over and over again. And then as the eclipse progresses, we see this layer rising up and then stopping and then coming back down again, which is the exact same Z shape as was seen in the Ham-Psi project. So that was my transmitter. And that signal was received by this gentleman here, DL3PB, who was in Germany, but he was using a Kiwi SDR receiver, so an online receiver, which also was linked to a GPS system. So that was also very tightly frequency controlled. And he managed to record the signal as it progressed through the eclipse. So both my transmitter site, the point of reflection, and the receiver were on the eclipse path. So we managed to replicate the Ham-Psi experiment, which we're very pleased about. And I think we actually got some quite good detail in here. I can see 2 lines within there, and I'm still trying to fathom exactly what's going on with that trace. I think we're getting a second path coming in there, but some more thought required. So the kit was from QRP Labs. It's called the U3S, and they're just about to add that to the QMX as a software update. So, yeah. Yes, it makes it very, very accessible to do home-based experiments in this. And that will also whisper transmitter and anything that's a frequency shift mode that will do. Okay, next slide, please. So to summarize, it's really handy to know the basics of propagation. It's useful to know what point in the cycle you're in, whether bands are daytime or nighttime bands generally of where you're trying to transmit to, and your equipment, your antenna height, your takeoff angles, things like that. On a day-to-day basis, it's really useful to know what the sun's up to on any given day, to know the solar flux. That's a 0 to 300 level, and if it's above 150 for 3 days in a row, you know you're on for a winner. Sunspot number is also useful to SN is the more immediate one, and be careful, some of them can be up to 6 months averaged. And the level and trend of the K index is also very impossible. So very, very important to know. So you need to know which way the K index is headed as well as its level. But the best advice, I think, is direct observation. So advice can be to listen to the bands and to keep tuning up until you no longer hear any DX, but that's going to take some time and things can change fast. So you can also use Whisper, or better yet, reverse beacon network. Actually see who's online at the moment. PSK reporter as well, very useful digital modes. And that's it. Thank you very much. Any questions? Yes. Yeah. Group.io. Yep. Groups.io. Yep. Which was the group for that one? Let me think. That was on one called QRSS Nights, which is a small group of people who send out these signals constantly and look for solar flares and how they affect the Doppler shifts that cause blackouts and things like that. Yep.
Hey Ben, this is Aurora. I got a question.
Hi, okay.
First of all, fantastic talk. I learned a lot.
Thank
and I'm just in awe of your citizen science experiment. I think that's so cool. But so like this is like, do we like your antenna like lobe, like base, how high you get off the ground plot? Do we know like why that happens? Like if you come over like the physics explanation of why that happens, or is this one thing for like this just happens and we're very good at describing it but not sure exactly why?
Well, it would have something to do with how the electrical ground and the waver coupled, I think. I'm not exactly sure off the top of my head why that occurs. I guess a dipole in free space would tend to radiate in all directions. So it's being squashed down somewhat by its proximity to the ground. Yeah, I'd have to think a bit further to come up with a better example than that. But I think as you go very low, it's pointing up. So it's the signal's tending to move away from the ground. As it goes higher, the signal's coming down. And then as it goes higher, yet it's fragmenting. So yeah, I think the signal's moving away from the ground is my interpretation of it.
Well, I would sometimes run a wire on the ground under into this antenna.
Yeah.
Things that's
Yeah, yep. Yeah, I happen to have a metal roof barn just behind it, but I think it might just be accidentally right in the right place. It seems to do a good job. Ah, yes, of course, the fraction of the wavelength. Right, okay. Right, okay. Yeah, I don't know if you caught that, Aurora, but so the fraction of a wavelength you're apart creates a push force, is that right? Or a pull force, yeah.
Thank you for repeating because I couldn't hear it from
Okay.
back of the room.
Great, okay. Anything?
All right, well, I guess that wraps things up for this evening. One more round of applause for Ben.
Don't forget to bow your cable. Unfortunately, only one person can bow.
Yeah.
That map, if anybody wants that map.
Next time, don't forget that.
All right. So sign up for the picnic and put a bid in for the map.
Also, for anyone on Zoom, if you want to sign up for the picnic, just email either myself or Bob, and I'll pass it on to Bob. And also, I realized I forgot to mention, if anyone is interested in the project we've been doing at Wilson's house in the Land of Magic, where we've scrapped TV parts and have been turning it into power supply and oscillators and stuff like that. The next date for that is going to be the last Saturday in April. April 26th.
last Sunday.
Sorry, what?
Sunday.
Sunday. I don't know what day or time it is right now. And then the second one is May 17th. So both Sundays at 3 p.m. Hey, have a nice night, everyone.
Just wait till his baby comes. He'll be more confused.